Let's talk about the rate expression and the rate constant now. The results in table clearly shows that the rate of the reaction decreases with the passage of time. You are able to see the rate of the reaction is reducing. As the concentration of the reactants decreases, this is decreasing, the time is increasing, and the output or reaction is reducing. Conversely, rates generally increases when reactant concentration increases. So, the rate of the reaction depends upon the concentration of the reactants. From here, if you see here, when the concentration increases, the rate of the reaction will start increasing. Here is a general equation. I got A and B as the reactants, which gives C and D as products. A, B, C and D are the stoichiometric coefficients of the reactants and products. The rate expression for this reaction is rate is directly proportional to A power X into B power Y, where exponents X and Y may or may not be equal to the stoichiometric coefficient of A and B respectively. So, the rate is directly proportional to A power X and B power Y, which indicates a rate equal to K into A power X into B power Y. Rate can be differentiated or given as minus d of R divided by dt. The reason is it's reducing, it's moving down, is equal to K into AX into B into Y. This equation is called as differential rate equation, where K is the proportionality constant that's called a rate constant. The equation like 1, which relates the rate of the reaction to concentration of reactants, is called as a rate law or rate expressions. Thus, rate law is the expression in which the reaction rate is terms of molar concentration of reactant. Each term rise to some power, which may or may not be same as the stoichiometric coefficient of the reacting species in a balanced chemical equation, which is given by this particular equation. So, I got nitric oxide reacts with oxygen to give nitrogen dioxide. You are able to see at one period you got 22.4 liter as the equal value for indicating 1 mole of any gas at 1 atmospheric pressure at 0 degrees Celsius. So here is the example. We can measure the rate of this reaction as a function of initial concentration, either by keeping the concentration of one of the reactant constant and changing the concentration of the other reactant changing, or by changing the concentration of both the reactants. You are able to see the concentration of the reaction, it's decreasing and it become constant at a specific period of time. Here is the following results obtained. The initial rate of formation of nitrogen dioxide. So its initial volume and initial rate, and the next volume and next rate. So nitrogen plus oxygen gives nitrogen dioxide. Based on the reactants, automatically the product will be obtained. Here is the rate. It is obvious after looking at the result when the concentration of NO is doubled. The following results are obtained. O2 is kept constant when the initial rate increases by a factor of 4 from 0.096 to 0.384 mole per liter per second. This indicates that the rate depends upon the square of the concentration of nitric oxide. You are able to see, if I double this one, this is constant. If I double this one, here it is a 4 times double. If I double this one, if this is constant, if I double this one, you are able to see it's a 4 times it's multiplying. So when concentration of nitric oxide is kept constant and concentration of O2 is double, the rate also get double, indicating that rate depends on the concentration of oxygen to the first power. So the rate equation for this reaction will be rate is equal to K into NO2 2 and O2 1. So this is 2 and this is 1. The differential form of this rate expression is given as minus d into R divided by dt is equal to K NO2 and O2. I am trying to show you a 3D of how the hydrogen and oxygen is mixed out to give the water molecule. Once hydrogen and oxygen is there, once the temperature is increased, automatically the atoms will become segregated and afterwards in the normal temperature it will become a water molecule. Let's see how it works. You are able to see the normal hydrogen and oxygen molecules here. Now the temperature, once if it is increased, automatically you are able to see there is a fast movement of molecules in the increase in temperature. You are able to see the molecules are separated in increase in temperature. In the normal temperature you will be having a normal things, but increase in temperature the molecules are segregated. You are able to see H2O2 before and afterwards it will become H2O. So this is called as a reactants and this is called as products. So the bond between the atoms are segregated, it's divided and becomes H2O now. This is how your water molecule is created. As you know, oxygen got 2 bonds, here oxygen got 2 bonds. Hydrogen got 1 bond, the same thing is here. This is referred to as reactants. The starting point of a reaction is called as reactant. The output of the reaction is called as products. So H2 and oxygen O2 becomes a H2O. But the thing is like we don't have a balanced equation because O2 is here but O is here. So we need a balancing equation. So H2 plus O2 becomes H2O, but still we don't have a balanced equation. So since we got 2 hydrogen, 1 and 1, 2 hydrogen and oxygen, we become 2 water. So we need 2 here. So 2 hydrogen becomes 2 H2 plus O2 gives 2 water molecules here. So we need 2 here. So this is called as balancing the equation. Now the equation is balanced. Here you are able to see oxygen and this is 2 oxygen here. And the number 2 here indicates the coefficients. So 4 hydrogen is here, 2 into 2, 4 hydrogen is here, it's balanced. Over here, oxygen 2 and here oxygen 2. You are able to see 3 molecules becomes 2 molecules here. So the number of molecules in the reactants is more. It got 6 atoms. But if you think about it, you are able to see the same thing happens, 6 atoms. So both are of equal. Same amount of hydrogen and oxygen becomes water here. There is no loss in this particular equation. So this equation is called as conserved. The reason is we don't have any usage of atoms in this reaction. So this is called a conserved reaction. So you are able to see 4 hydrogen atoms are there, and let me check it out. 3, 4. Obviously we got 4 hydrogen here too. Then what about oxygen? 1, 2. Here 1, 2. 2 oxygen atoms in both the ends. So this shows the law of conservation of mass, which indicates the total number of reactants is equal to the total number of products. That's referred to as law of conservation of mass. Here are the reactants, hydrogen and oxygen. Which becomes product water here. So once again repeating it, like I got my hydrogen H2 and the symbol of oxygen is O2, becomes water H2O. Here we got 2 hydrogen and 2 hydrogen. It's balanced. But we got 2 oxygen here, but over here I don't have 2 oxygen, only 1 oxygen is here. I am trying to show you like how a simpler chemical equations are balanced. If I am putting a 2 here, it's not possible. So obviously I need to put 2 here to make it 2 oxygen here. If I make 2 oxygen here, the hydrogen becomes 4. So obviously to balance this equation we need this hydrogen to be balanced by multiplying with 2 to make it 4 hydrogen here. Now we got 4 hydrogen atoms. So both are balanced. We got 2 oxygen atoms, both are balanced. This is referred to as balanced chemical equation. I am trying to show you some other equations which is balanced with the coefficients CH4 methane, it's ammonia, carbon dioxide, methane with oxygen, carbon dioxide and water, and this is your water, hydrogen fluoride, hydrogen chloride, phosphine. So the differential form equation is given as this one. We observe that for the reaction in the rate equation derived from the experimental data. So the exponents of the concentration of terms are the same as the stoichiometric coefficient in the balanced chemical equation. This may happen 1 and here 1. Both are same. Let me explain you the structure of an element. I have taken the methyl trichloride. It got 3 chlorines and 1 hydrogen. So the molecular geometry is defined by VSEPR theory. So I got A, X, N. The number of element is N. We'll remove this one. So based on the arrangements of the number of atoms, the design or structure of an element is. Here is the formula and the shape and the bond angles. Since I got A, X4, so it will become tetrahedral with 109.5 degree as the bond angle. We are able to see the structure with a bond angle of 109.5 degree. So 109.5 degree. It will be having the same angle on all the directions. In some other example as below, the reaction is different. You are able to see the experimental reaction. Trichloromethane with the chlorine got carbon tetrachloride with HCl. So this is the equation. Over here the rate is, this one is single. If it is increased, 1 times there will be an increase. If it is increased or it is reduced, it will be increasing. It's half times it's increasing. The rate of reaction is 1 here and this one is half. Here is the molecule 3D of ethyl acetate. So in between the carbon atoms you got the double bond and you got the single bond in top and bottom. The structure of ethyl acetate. Now I got a typical example with water. I got ethyl acetate with water gives acetic acid and ethanol. Over here your ethyl acetate will be having the rate of reaction as 1. For water its neutral value, it's 0. Whatever water you are adding, you won't get anything here. It doesn't have any major impact. This is referred to as rate constant values. So in these reactions, the exponents of the concentration term are not the same as their stoichiometric coefficient. Thus, we can say that rate law for any equation or relation or reaction cannot be predicted by merely looking at the balanced chemical equation. Theoretically, but must be determined experimentally.